Hi, this is ET350 Lecture 20. Today we're going to talk about single-phase induction motors, and we're going to build off that lecture or the previous lecture on the spinning magnetic field and that mathematical description of B. We're going to introduce this motor called a shaded pole motor, and we'll do a little demo. And we'll talk about the capacitor run start motor, and we'll look at a single-phase and a two-phase motor. We'll follow it up with an example and then a simulation and demo as well. So let's begin. Okay, so single phase motors. Well, what do we normally have? We have three-phase motors, and the three-phase are nice is because it delivers smooth power at any instant, right? The addition of all those three currents and three voltages oscillating at 120 degrees apart will give you an instantaneously smooth voltage. But single phase is common in households. And so if you don't have three phase, can we trick a motor to spin with only one phase, right? And like I said, we're going to explore these two types, shaded pole and capacitor run start. So let's look at the shaded pole motor. And so the shaded pole motor is a single phase, and it uses a copper inductive band, okay? And this copper is what is able to create a spinning magnetic field. And so it's inefficient, but it's simple, and it's simple to manufacture. It's cheap. It's good. And so here's a diagram of what we got going on. You have your 120 volts coming in from the wall, AC, and you have a coil. And so this is essentially an electromagnet, and it's going to create flux that just goes up and down, up and down. Now, if you don't have these copper bands, that means the flux in here is just going to go up and down and up and down. And what you'll typically have is a squirrel cage rotor inside. And what these bands do will lag. If you remember, it'll lag the flux, and you'll get a spinning magnetic field as opposed to one that just goes up and down, up and down. What does one look like? Well, one looks like this. Okay, so here's an example of a shaded pole. Let me turn on my light here. A shaded pole induction motor. And you can see the copper bands right here. You can see the big coil, right? The big coil right there. And you can see the two 120 volt leads. All right, let me focus in on that. Perfect. Okay, and right here in the middle is the induction rotor. And for this one I believe was a microwave fan motor. All right, so you got your shaded pole here. Without those copper bands, the magnetic field would just go up and down, but with the copper bands, it actually spins around and around. And so what does that look like? So let's rotate the page here. And so imagine you had one phase of AC current. And so this AC current is coming from your 120 volt source. So this is one phase, and you just have one period, let's say, right? And let's imagine what's going to happen. So if you have no shaded pole at this point here, you're going to have just, let's say, a magnetic field that goes up, all right? Now, what's going to happen is that this shaded pole lags, right? It's going to lag whatever the current was before. And so in this corner, you're going to have the full normal 100%, flux density going this way via Ampere's law, right? But then this one is going to be smaller, and it's going to be forced this way. So it's going to be lagging a little bit. So your overall flux density is a little bit canted to the right. Okay, so what about at this point? Well, the current is going to go down. But remember, the previous one is big. So that means the shaded pole is now going to allow the flux that was held and shoot it out, right? Because it's lagging, right? But now the current flux density is a little smaller. And so if I took like kind of the vector addition of both of these, maybe I'm either straight or canted a little bit to the left. If I had no shaded pole, I'm just like a little guy, right? Okay, what about over here at this point? Now I have negative current, which means I'm going to flip the direction of the flux. And so I get something that looks like this, pointed down if I had no shaded pole. But what about over here? Well, what's going to happen is the current magnetic field is going to go down, but then remember the shaded pole is lagging whatever the previous was. So maybe the overall flux density is pointed to the left, right? So you can start to see this rotation. When we get to the point of maximum flux density but negative, or maximum current but negative, you would get this, right? Which means that this maximum current would create a maximum flux density in this direction, and your shaded pole would delay from the previous. Okay, let's keep going. So now it's negative. It's the same one as this one, right? The only difference is the lag on the shaded pole is not the previous lag from this one. So yes, the diagonal looks the same, but the shaded pole is now taking that maximum and sending it this diagonal way. Okay, and then let's go here. Now we flip the current, so it's positive again. So now flux density is going up, and we have it going up like this, but the lag is now pushing it to the right still. So we have an overall flux density going the right, and the last one, we're back to where we started. Okay, and so you can see that this magnetic pole or this magnetic field inside the rotor did a full 360-degree rotation, right? So that's how essentially the shaded pole induction motor works. So let's do a demo while we have this here. So I have this guy here, and you look at this, and maybe it's to me it's a little scary. It's like, wait a second, we're taking 120 volts and putting across just this coil. That's it. I mean, yeah, there's a lot of turns, but that looks very thin. That looks like it's going to burn these out, right? You know, I got these thick, beefy wires, and then it's going to go to these thin little baby wires. That's nerve-wracking. Why would that be okay? And plus, there's not going to be a lot of resistance. There's not going to be a lot of resistance, right? If it's just a short, yeah, maybe it's a long wire, but the R is not going to be big. Well, don't forget, this is AC. So because this is AC, what do we got going on? J omega L. The Z, the impedance for inductor, is J omega L. So if it's 60 hertz, the omega is actually 377. So you have 377 times whatever inductance is going on. That can be quite a bit of ohms, even if the inductance is quite small, right? So yeah, let's try it. So we can spin this up. So I have my power cord in here. Okay, so let's plug it in. Okay, so I have my power cord here. And why don't we flip this around so I don't spin up all the papers. Get this wire out of the way. Everything's good. Okay. All right, so ready? And not too bad. And that's what you would expect. Okay, do I have a little, can I see the RPMs on here? Yeah, 1200 RPM. Okay, kind of cool. So you can see the RPMs, 1250. Yep, cool. Right, so it's spinning up at a decent amount, and that's it, right? Actually, can we measure the current? A little current meter here. So I can take this current meter, right? You can see that right now it's 0. And if I put it over both, do I get a reading? I get nothing, right? Because I'm putting over both. But if I separate and put it over one, what do I get? Let's see here. Did I get anything? Very little. I'm seeing very little here. Let's see if I can get it under here. Very little current. Maybe it's not sense. Oh, I got on the wrong setting. Current here, 2.3 amps. Okay, so reasonable. Good. Okay. All right. Unplug that. Cool. So that is a demo of a shaded pole motor. Cool. Okay, let's move on. So let's look at a capacitor run start motor. Okay, capacitor run start motor. And so we're going to look at two different types. One is just single phase. And what we'll show is that in a single phase induction motor, we will show that we actually get two opposing spinning magnetic fields. And this would need a kickstart. Okay. And we'll look at a two-phase induction motor that is actually created from a single phase. And we can convert a single phase to two-phase using a capacitor. Remember, a capacitor will actually help you lead the current, right? And we can create a 90-degree phase shift. And recall this from our last lecture. This is our stadium wave analogy equation. B total equals B max cosine of omega t minus P over 2 theta s. And that's when we had three phases and all good. But this actually would describe, doesn't matter if you three phase or one phase or two phase, if you are able to see this relationship, this is telling us that we have a magnetic field that spins. Remember, theta s is like some fan in the stadium, right? And omega is related to the electrical frequency, and it's also related to the speed of the spinning magnetic field, right? Okay, so notice the minus here. If I were to flip that to a plus, that's the equivalent of changing the direction of the magnetic field, Okay, so remember this equation here, if we saw this, this would describe a spinning magnetic field. All right, so let's look at a single phase, 2-pole cylindrical wound induction rotor stator. Very simple. And you can already imagine, just like that shaded pole, if you had AC current, this magnetic field is going to go boop, 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 left and right, left and right. Okay, nothing really exciting. But really what's going on, it's actually two magnetic fields, and we'll see it's mathematically true, as spinning, but in opposite directions. So this single magnetic field doing this back and forth is equivalent mathematically to two rotating magnetic fields spinning in opposite directions. So if you recall from the beginning of our last lecture, if we just had static current, and we measured the magnetic field at different angles of theta s, we would see B equals Bm cosine of P over 2 theta s. And we proved that last lecture, right? And you can see it here. If I'm here at 0, cosine of 0 is 1, I'm going to get the max B. If I'm here at 90, you can see that this goes to 0, right? No magnetic field. Here I get magnetic field, 0 magnetic field, back to 0. Okay. Now, if this is AC current, we know that the AC waveform looks like a cosine. We know from Ampere's law the intensity of this B is proportional to I. And we can now take this going into here, this AC current equation going in here, and this going into there. And we did this before in the last lecture. So now we have two cosines, and we can use a nice trig identity. The multiplication of two cosines is equal to the addition of just subtracting the arguments, A minus B and A plus B, okay? What we can do is now replace this. So if A is omega t and B is P over 2 theta s, we can just replace this with this version, and we just add the 1/2. So A is omega t, B is P over 2 theta s, we plug it in, and we get just this, very simple. K IP over 2, K IP over 2, times cosine of this guy, A minus B, good, and A plus B. And like I said before, if we see a sign switch, it's saying that the magnetic field is spinning. So this is describing two opposing magnetic fields, okay? What does that mean? Well, that means it can't self-start, but if you give it a kickstart, it can start spinning in either direction, right? So you apply AC current, okay? And a lot of these capacitor run start motors, if the capacitor fails, you'll be plugged in, and if you gave it a kickstart, it'll actually keep running in either direction, which is kind of neat, okay? And we'll actually do this demo at the end. Okay, let's keep going. So now let's look at a two-phase, two-pole, and we'll see that we get a single magnetic field. So now let's say I have an A and I have a B. And let's say for A, if I have positive current, I would get current going into the board and coming out of the board. Same with B. If I had positive current, I'd have current going into the board and coming out of the board, right? So if I had positive A current, what's going to happen? I'm going to have a magnetic field that goes to the left. If I have positive B current, I'm going to have a magnetic field that goes down via Ampere's law. Okay, so notice the coils are mechanically rotated by each other by 90 degrees. Okay, not 120 like in the three-phase, right? And so what we can do is we can write these two equations. Okay, KIA cosine theta s. Now there'd be a P over 2, but we said 2P, so that goes away. Okay, so notice I get a 90-degree rotation here in my magnetic field equation, right? So this one is exactly the same as this one here. This one is the B coil, but it's just rotated 90 degrees. Does that make sense? Let's double check. If theta s is 0, what are we getting? We're getting a 90 in here, and cosine of 90 is 0. Good. That should show 0. Good. Okay. So now what do we need to do? The current. So yes, we can apply electrical current AC, but we got to do a special thing for IB. We have to shift it by also 90 degrees electrically. Okay. So this is just 0 degrees phase. This is 90 degrees. So this, whatever this is, this has to be 90 degrees leading this one. Okay. We can play the same game where we add the 2 to get the total. This is very similar to the three-phase. The three-phase was actually much more complicated. Remember, in the three-phase, we had 120 and 240, and then 120 and 240. Well, this is just 2, 90, 90. That's it. Okay, so we're playing the same game. So this is the A and this is the B, no problem. And we can use exactly the same trig identity and just see what we get. And we notice if we plug in This is for the A and the B. We get a cancellation of the 90 here, and we get an addition of the 90 there, right? This is just for the A, no problem. So the cancellation of the 90, we get an omega t minus theta s, which is going to combine with this one. And this one, we get a 180 here. What does that mean? Well, we're going to get a 2. 1 plus 1 is 2, good. But then we're going to get a cosine of omega t plus theta s, and we're going to get a cosine of omega t plus theta s plus 180. Now, what do we notice about this 180 guy? If you have a phase shift of 180, isn't that equivalent to just a sign change? It is, right? Cosine of theta plus 180 is just the same as a sign change, right? Just make it negative, right? If you shift something by 180, then it's the equivalent to just flipping it over the axis. Okay, that's good if it's periodic. Okay, all right, so what do we have here? Notice these guys go away. They cancel out. And so you're just left with this one, KIP cosine of omega t minus theta s. And if we see that equation, we know we have a single spinning magnetic field. And so this is a way to take single phase and chop it up into one extra phase, one auxiliary winding that has an extra 90 degrees phase lead, both mechanically and electrically, and we get a single spinning magnetic field. Okay, this was maybe the more rigorous mathematical proof. Could we just go more graphical? Let's look at a graphical approach. So let's look at that same thing. Okay, so I have the same coils here. I have A and A prime, B and B prime, right? And like I said before, if A is current is positive, B is going to the left. If B current is positive, is going down. Okay, that's right. And let's just look at what IB and IA would look like if IB is leading by 90 degrees, right? That's just showing this current right here. This one. Okay. All right. So IA cosine of omega t, good. IB cosine of omega t plus 90, good. It's shifted to the left, it's leading. And let's imagine what the magnetic field inside this stator would look like as I progress down these numbers, 1, 2, 3, 4, 5, 6. Okay, in this point at number 1, what's going on? The current is positive in the B coil and 0 in the A coil, and it's going down. Okay, so let's do this. It's going down. Good. Now, if we go to the next point in time, then the current is positive in the A coil and 0 in the B coil. So now it's going to the left. Good. Now what about the next point? Now it's negative B, so it's actually going up. Good. And then what's next? We have the current going in the A coil, but negative, so it's going to the right. Good. And now we're back to where we started with the current going down, and then we can go to the next one and just repeat so on and so forth. So you can see the spinning magnetic field. So hopefully you're convinced that mathematically and graphically, you're seeing the same result, that two-phase where your coils and your electrical current are shifted by 90 degrees, you're getting a single spinning magnetic field. Kind of cool. All right. So how would you convert a single phase to a two-phase? Well, what you could do is, if you only have one source, you can add a capacitor, and that capacitor will get you a 90-degree phase lead, right? And so this is what we want. So let's say I equals IP cosine of omega t plus theta. We could have a non-zero theta here, and IB equals IP cosine of omega t plus theta A, and then plus 90. So that means theta B is whatever theta A is plus 90, right? And so this would be our objective. Theta B equivalently written as the angle of IB, these are the same things, is equal to theta A, which is equivalently written as the angle of IA plus 90. So this is just saying the current IB is leading this one by 90 degrees. Easy. So how would we draw that as a circuit? It would look something like this. So this coil here would be this coil, right? And representing that coil as a resistor and inductor. And this coil here, B, would be represented by this one, but we would add a capacitor in series to shift this current to a leading situation. And then we'd have your 120 volts coming in. And then the rotor would be inside, okay? R and L are just the resistance and the inductance of the coil, no problem. Okay, we'll do an example on this later. So there's so many different types of capacitor run, capacitor start motors. This is just two. So you could always leave the capacitor connected. And so you have just essentially what we have. This runs smoother than just start. And it's efficient. It's more efficient, but maybe not as good starting torque. But what you could do is actually add another switch, and you could have a second capacitor here. So this is if you needed some good torque at starting, this would help you out. Now, is this more expensive? Yeah, because you got to have a switch and you have to have an extra capacitor. But this might help you out, and then you switch it out so that you run with the smoother, more efficient capacitor. That makes sense. Okay, so these are just different flavors, so many different flavors, but I just want to give you in this lecture the main idea of how a capacitor run motor starts. Now, in practice, these capacitors are the things that fail typically, right? And so that's something to look out for, right? So if these things fail, it's probably just like, well, okay, go to the spec sheet, find out the capacitor that it was using, go buy a new one, click it in, and you're off and racing again. Okay, this switch is typically like a centrifugal switch. So it's detecting the speed in some way. It's mechanically detecting the speed, and then it switches out. So I found this nice lecture, EP7 by Mr. Adnan Mohammed. And here's a picture of a capacitor run motor. See the big capacitor on the side, you have your induction motor. Okay, and so of course you have two windings. You have your main A winding and you have your auxiliary B winding. Okay. And here's an example of what's going on the inside, right? It's just a normal induction stator. And you can see that they have the coils either, shifted by some mechanical amount. And you have your rotor with the centrifugal switch on it, okay? And so what does that contact look like? Well, if you look closely at this drawing, okay, what's happening is this. You have your start winding, your auxiliary winding with your switch, which is that switch here. And you have your main winding. And let me see if I can move my camera here a little closer so you guys can see it. Okay. So this is connected to the shaft. And imagine when the shaft is not spinning very fast, this spring is in, right? The spring force is pulling this in, okay? And it's these contactors that are keeping the capacitor in are closed. Now, as this thing starts spinning faster and faster and faster and faster, then centrifugally these things start parting and coming away, right? Okay. Now the spring wants to keep it in, but it's overpowering the spring. As this thing starts moving away, this whole mechanism starts sliding to the left. Okay, which means this contactor loses contact, right, and opens up the capacitor. So this only happens at high speed. So this is an example of a centrifugal movement on a switch. Okay, all right, good. Okay, and that would be connected right there. All right. So let's do a simple example. Let's say we have our simple capacitor run motor. We have the capacitor, the resistor, the two coils, the A coil, the B coil. These are your auxiliary windings, your 120 volt source, and your rotor. Okay, and you're given 120 volts RMS. Let's say it's 60 hertz, which is omega equals 2 pi f or 1 tau f radians per second. This should be, I think, 377, right? Let's say they say the resistance is 10 ohms and then the inductance is 31.6 millihenries. Okay. And they ask you, well, why don't you solve for a capacitor such that you're going to get that 90-degree phase shift? IB leads IA by 90 degrees. Okay, and then once you've computed that C, why don't you just double check what is the magnitude of A and the magnitude of B with the new C, okay? And so what would be a strategy? Well, the strategy could be solve for IA using our complex Ohm's law, right? You can put these in series and solve for this, right? You can do the same thing for IB, and then you can enforce this equation, right? Where IB equals IA plus 90 degrees or pi over 2 radians or tau over 4 radians. And then just solve for C using this constraint. Okay, so let's do it. Let's do it. So let's say we can apply our complex Ohm's law, right? So let's see. So our complex Ohm's law, if you recall, you have this by KVL, this V comes over. So I goes into the positive terminal, right, of V. And this is your big R, your Z, right? And they're in series, so you can add them up. So your IA is V over Z, right? This guy here, if you recall, is your ZL, which is just J omega L. And because they're in series, you can just add them up. Okay, seeing this over and over from 250. Hopefully it's not too bad. Okay, now if you remember, if I want to find the magnitude of this, I got to get the magnitude of the top or the magnitude of the bottom. Well, the magnitude of the bottom is just what? The Pythagorean theorem, R squared plus omega L squared square root. Okay, What about the phase? Well, you can take the phase of the top minus the phase of the denominator. The phase of the denominator is not too bad. It's the inverse tan of the imaginary part over the real. So that would look like this. 120 over square root of r squared plus omega L squared for the magnitude, and 0 degrees given for the phase here, and tan inverse of the imaginary over real. Notice you don't put a J in here, just a good reminder. Don't put the J in this calculation, right? That'll mess you up. It'll add an extra, what does it mean to do tan inverse of J? And yeah, don't do that. Okay, so this is the magnitude part and this is the phase part, okay? And notice these are all numbers that we could, we can punch in. In fact, we don't even need the capacitor in here. We could actually calculate what these are, what this is, right? Okay, in the next one, we can do IB. The only thing that changes is that we're going to get an extra capacitor term, okay? And so we have this. Now remember, the capacitance is 1 over j omega c, but if I bring j to the top, I put a negative there, okay? Everything's in series. And so it's the same thing. What is the magnitude? It's Vs divided by the square root of the real part squared. Now this whole thing is the imaginary part squared. Good. And so that gives you this, right? Okay, so 120 over the square root of r squared plus omega L minus 1 over omega c squared. Good. And what about the phase? It's 0 over the inverse tangent of, okay, what do we have? Omega L minus 1 over omega c divided by r, which is this, omega L minus 1 over omega c over r, tan inverse. Now I forgot to mention, look at this. When I calculated the overall phase of this, notice I had 0 minus. And that's where that minus you subtract when you divide. That's where that minus comes from. It's the same thing here, 0 minus. So when I look at the phase of B, I'm going to have that minus here. Okay. And so this is the magnitude. This is the phase. Notice no J in here. And I should say it over here. No J. Okay. All right, good. So these are just general equations that we are going to use. So what was the first thing? Compute the capacitance here using this constraint. So what I'm going to say is IB is this equals IA is that plus 90 degrees. And it's pretty straightforward. It just ends up being one equation, one unknown. Okay. So all I'm doing is plugging in is IB in there, or angle of IB and angle of IA in there. And you can see we have omega LRC, omega LR 90. All those are known except for C. We have one equation, one unknown. Okay. By the way, how did we get omega? 2 pi times F, 377 in this case, right? Okay, so to solve for C, okay, the rest is just algebra here. What do I have to do? Okay, I can take the minuses, so plus, plus, minus. What else can I do? I can take the tan of this whole guy. All right, good. So I have the tangent of all that, right? Okay. What else I can bring the R over? Great. Okay, no problem. Bring the R over. Look at the C here. I can flip these. Okay, so I get 1 over omega C equals omega L minus this. Okay, no problem. And then look at this. I have the C here. I can trade places with this entire term in that. Just some simple. Yeah, it looks crazy, but there's nothing in here that's beyond your capabilities here. So these are all just numbers. 377, 10, 31.6. Plug them all in, see what you get. And this is the C that satisfies this result. And in this case, we get 1.3 times 10 to the minus 4, or 130.6 microfarads. No problem. We can plug these back into these magnitude equations, and we would get the current. So what is it saying? 9 and 7 amps. Notice we're getting a bigger current in the B branch, right? Because that capacitance is actually dropping the impedance because you have the 1 over omega C. So we're getting more current, okay? So just because you get a nice 90-degree phase shift doesn't mean you're getting equal current magnitude. So that's okay. All right, so let's look at a simulation, and then we'll come back and we'll look at a demo, right? We'll actually demo this. So I'm going to share screen to my simulation, and I'm going to have the same numbers. And so here we go. We're looking at the simulation here. And what do we have? We have 120 volts with RMS, which corresponds to 169.7 volts peak at 60 hertz. Good. And I have the A branch and the B branch. And the A branch, what do we got going on? 10 and 31.6 millihenries. Same with here, 10 and 31.6 millihenries. And I put in the capacitor, the one that we solved for, 130 microfarads. And you can see if I reset and run this, you can see that we are getting the phase of the IB branch current to be leading by 90 degrees. And notice the amplitude of the current is going a little bit more. if I were to change this capacitor, things would get a little wonky. It wouldn't go in phase anymore. You get some weirdness, right? Look at that, total weirdness. Ugh, gross. So let's put it back to what it was. Nasty. Okay, so 130.6. Right now you get that nice current. So there is some balance that you guys got to play with that to make sure that this all works nicely. Okay. But yeah, this is just a very simple little simulation of the results that we got, right? And you can see how the current is flowing. Let me slow it down a little bit just so you can see what's going on. You can see the current in the B branch is leading. This goes first, then this follows, then this goes up, then this follows, right? And so everything hopefully is matching our intuition. And this is what's creating our spinning magnetic field. Okay, so let's go back and let's look at a demo. All right, so what do we have here? I'm going to clear this out and careful here. And what I'm going to pull over is, look at that. It's a capacitor run motor. It's an induction motor. This is ripped out of a fan, actually. And so what do we have? We have two sets of coils. There's an A and a B coil. We actually have it's hard to see, but there's an induction rotor there. Okay, it's got the squirrel cage motor. All right, and there's a little baby capacitor right here. Okay, and I have off and on, off and on. This one had multiple taps so that you could change the speed, but we just worry about the two. So these are the two that would go to the source. And if we just run it, this has a kind of cool little gizmo here. It has the oscillation mechanism. So as it's spinning, it's also turning this so that it oscillates back and forth. Kind of cool. That's all embedded in here. Okay, so if I apply 120 volts to this and I have the capacitor on, this will just spin without any issue. Let's do it. So let's see. I have a nice cable right here. Okay. Now, pro tip: notice how the leads are not the same length. They're a little different. Same with here. The leads are a little different, right? That way they don't short when they touch. In fact, I can even do that, right? And so what I can do is I can connect this lead here, and I can connect this lead here. Okay. So I'm going to put this like this, and I have the capacitor on, and I can plug in to. So I'm going to put that there. I can plug into my power supply. So it should just spin up. Very good. Okay, no problem. Now, like I said before, if I turn this off, this capacitor off, we're back to a single phase. And remember what I said? If we have a single phase, we have two spinning magnetic fields going in opposite direction. So with the kickstart, I actually can keep it spinning. So if I turn the capacitor off, it will stay spinning. And it's still spinning. It's not as much torque, but it's still spinning. If I turn it back on, okay, it's spinning, and I can feel the torque. Like if I'm trying to slow it down, it's definitely resisting me slowing down. Okay, and we can check the speed. Let's see here. Let me get it on, and we're getting about 1700 RPM. That's good. There's a little bit of slip. I believe this is a 4-pole motor, so 1800 RPM is the synchronous speed. Good. So everything is consistent. If I turn it off again, look what happens. I can actually stall it. AC current's running, but I should be able to spin it up again. That's kind of cool, right? And I can feel it spinning up. I know it doesn't show very well in the camera, but you can tell that it's spinning. Okay, I can slow it down, and I should be able to, if I can get it fast enough. There we go. We can spin it the other way. I'm not very good, but I think you guys get the idea. All right, well, I'm going to cheat. There we go. I added the capacitor. So single phase works with the capacitor off. Boom, capacitor off. It's continuously spinning. And two phase works where the capacitor is adding that 90-degree phase. Kind of cool, right? So I hope this demo showed you how a capacitor run motor works, how it works still in single phase, and it works as a two phase with the 90-degree phase lead. Okay, I'm going to turn this off, power this off. Good. Okay, I hope you learned something. I'll see you in class.